Hey kids, today you get to see me as well as hear my voice. I feel like that's a little too much for every video, but this one in particular I wanted to do. This is one of my favorite lessons of the whole year. So there's some things that I want to actually physically show you. So that's why you have to deal with my face for this video. All right, so we are moving from area to volume, just like you did in middle school, right? In middle school, when you first learned how to find the area of a square, you eventually move to 3 dimensions and saying, okay, well, how do if I take the area and then just multiply it times the height, I get volume. So that's where we're going. So the big idea for actually the next 5 videos is going to be taking the idea of area and generating volume. And if you notice all the pictures down here, here's all the ways we're going to do it. And then throughout the next week and a half. So we're going to do volume with potato chips. Then we are going to do volume with lifesavers. Then we are going to do volume with bundt cakes. Are you getting hungry yet? And then lastly, I don't know why I put the pictures in this order. Lastly, we're going to do volume with Play-Doh. Now, this title here, volumes of, I meant to do the highlighter. Volumes of revolution only go with number 1, 2, and number 3. The Play-Doh method of taking area and generating volume is a volume, but it is not a volume of revolution. So that's why that's going to be last. And now let me give you the boring math words for this. Most textbooks don't say volume by potato chips. They say the disc method. They don't say volume by lifesavers. They say volume with the washer method. They don't say volume by bundt cake. They say volume by shells. Now, sadly, my bag o shapes, 3D shapes, is at school, and I didn't go and get it. But I have some things around the house I can pick up to kind of show you what I mean by some of these things. So here is a very mathy slide. To find the volume of a solid S, divide S into slabs of equal width. Think of slicing a potato. Now, sadly, I went to my pantry and I don't have a potato, but I have an apple. So think of slicing an apple, right? An apple is kind of sort of circular, right? But not completely. And this apple is very nice, but there's, right, more elongated apples and all that. But if I slice this potato, think about what the cross section would look like, right? It's not a potato, it's an apple. But look, see, I'm saying like this. And what if I slice it? Look at that knife. Yes, I bring knives into school sometimes, but I do it hidden. If you slice your shape, then these are very, very thick slices, right? But can you see that those slices, I am slicing down with my knife. Can I draw a knife? Slicing down with my knife perpendicular to the x-axis. Here's a slice, right? Perpendicular to the x-axis. And when I slice through it, that's one slice, and there's 2 slice through the x-axis, right? This is my dx, right? And when it's a large slice, we call it delta x. When we shrink those slabs very thin, we call this triangle x or delta x, this delta x, dx. So I have a little cylinder, really, when you cut it. Watch. Knife, apple. Cut. Cut. Right? This is like a little cylinder, isn't it? Right? Where, look at the cross section. What shape is that? Circular. Can you find the area of a circle? I think you can. Times how thick it is. That gives you the volume of this little cylinder. So look at my picture here. What is, right, the height? So the sum of the cylinder areas, just the cross sections, multiplied times the height. If you make thinner and thinner, oh, I almost got my finger. Right? If I find the volume of all of these little cylinders, area, circle, times width, and then I sum all of those up, well, don't I have a pretty good approximation of the volume of this apple? That's what we're going to do. We're just going to make these slices really, really thin. Now, here's something we miss. We miss a lot of things being in person, but you know what you also miss? I would have done this in person with a potato, and then I would have said, visualize making them really, really thin. What would you get? And you know what you'd say? You'd say potato chips, and I'd pull out Pringles, and I'd give everybody some Pringles. But I don't have any Pringles this time. I just have these things. But they are kind of circular, a little bit more than Pringles, right? But they're pretty thin, do you see? But that's that's still a cylinder. It's just a super, super thin cylinder. Off the eaten path. Veggie crisp. Snacks for the curious. I didn't even know I had what these were. They're okay. Pringles, sadly. Worse for you. Tastes better. Anyhow. Very mathy explanation of what I just did with that freaking apple. Right? You're going to take a solid and you're going to slice it up. And then you're going to sum. Look at what this says. Area times width. Area is 2 dimensions. Width is 1 dimension. When you multiply 2 dimensions times 1 dimension, you get 3D, you get volume, OMG. You take the limit as the number of those slices goes to infinity. That's the Riemann notation. Here's Leibniz's notation. I'm never sure if I spell his name right. The infinite sum, where you start making slices to where you stop making slices of a product, but the product this time is area. An area function in terms of x times the width of your slice, which is dx. Now, you learn from doing, right, the area between 2 curves in the last video that I could also take, where'd it go? My apple, turn it this way, and I could have sliced like this. If I sliced like this, my knife is perpendicular to which axis? Right? It's slicing down or across to the y-axis. So I also could have a volume that is an area function in terms of y, slicing towards the y-axis. So these numbers, C and D, is where you start slicing the lowest on the y-axis up to the highest, D, on the y-axis. Whereas if you're on the x-axis, it's the farthest left, stop, farthest right. Here, farthest down, farthest up that you're making your slices. Okay? So this is a nice little applet here. If you want to, this PowerPoint is in files. If you want to click and do a nice interactive applet, it's fun to kind of play around with and visualize. So let's start off. Now on Canvas is a handout with these problems on it so that you don't have to copy the problem down. So if you want to pause the video and go get that, I gotta get my face out of the way. So here are the key words that you want to highlight. I'm finding volume and I'm rotating. For now, it is always going to be rotating. But remember, I told you at the very first slide, we're going to eventually do volume with Play-Doh, and that is not going to be a rotation revolving situation. So keep that. So always highlight or underline that word. Also, here is the next thing that is super important. Where are you rotating around? So step one, draw your function. And start and stop there. So here is the square root of x going from 0 going to 4. Now, you then draw your axis of revolution. You don't have to write its equation, but that's going to be nice later, because later I'm going to shift that axis off of y equals 0 and maybe make it y equals -2, but not yet. So next question. Is there a space between my shape and the axis of revolution? The answer to this question today is going to be no. In this video, no. And here's what I mean by that. There's my shape. There's my axis of revolution. There is no space. There is not a blank space. Right? Do you see that? For today, that is always going to be true. But by the end of this unit, that is not always going to be true. So you have to figure out, what am I dealing with, right? What is my strategy? So for today, the answer was no. Therefore, next, draw a representative strip in your region from top to bottom. That is just like when you did the area between two curves. Now, in your region to your axis of revolution. 5. Sketch the reflection of your region over your axis of rotation. So, take this square root of x from 0 to 4 and draw it over the axis. Now, what you have to imagine, again, this, sadly, I don't have a visual, but like there's so many good Desmos and GeoGebra activities that show this. You need to imagine that you are taking the square root of x and you are spinning it. And you are spinning it through space. So I'm going to take this and I'm going to spin it out at you, down and around, back through the wall and around. Spin. That's your revolution. So spin. That's what I have. That's what I have, like this. I have a whole bunch of those all the way along as I, just like with area, if I click and drag all the way through here, I have a potato chip there, a potato chip there, all of these potato chips, and I'm going to take the area of each one cross section and multiply it times its infinitely thin thickness. And then I'm going to sum them up. So back here, when you answered no, that's how I know I have a potato chip problem. What do the boring books call that? Discs. Gee, should it be a C or an K? I don't care. I call it a potato chip. So 6. Every time, because you did a spin, every time the area of your cross section is going to be a circle. Every freaking time. So your area function you need to now write an area function in terms of x or y. How do you decide? Your knife. That's how you decide. How did I slice? Did I slice down or up? Doesn't matter, right? Am I perpendicular to the x-axis or am I perpendicular to the y-axis? Which are these slices? To make this slice, I had to slice perpendicular to the horizontal. So for me, I am going to be writing an area function in terms of x. So the area of a circle is shockingly pi r squared. But you need to write that function in terms of x. What is the radius of every single one of your circles? What is the radius? Right? The radius of every one of these circles goes from my axis of rotation up to the function. How long is that? How long is that radius? That radius. How long are all my radii? Root x, right? Which, of course, in this instance, simplifies to just pi times x, right? And now you're ready to integrate. Since my slices were perpendicular to the horizontal, I'm going to be slicing dx. I started my slices at 0 and stopped my slices at 4. My area function was the square root of x squared, so that's x times pi. I think I'll osmosis the pi outside since it's just a constant. Bam. And now integrate, hun. And that ain't no big deal, right? X squared over 2, put in 4, put in 0, subtract, multiply your answer by pi. So I'm going to erase all of this because I did type this stuff out. There's a prettier picture, right, of the volume, right? That's my shape. It's kind of like a sideways paraboloid. I sliced it up. There's my representative slice. There's the representative slice of my apple. There it is. Prettier than I could draw it. The volume of the cylinder is the area of the cross section, pi r squared, times that thickness. I know it says h, but remember that's a thickness as you're slicing along the x-axis. Bam. This was a very easy integral to do by hand. 4 squared is 16. 16 divided by 2 is 8. 8 times pi is 8 pi. Plug in the 0, you get 0. 8 pi minus 0 is 8 pi. They didn't give you units. You don't have to give them units back. Oh, my Lanta. Let's do another one. This is number 2 on that handout. So again, the key words that I'm looking for are volume, by rotating. I have square root of x, but wait, what's going on here? Y equals 1. Let me draw what's going on here. I have the same freaking shape, but it's smaller, isn't it? I told you I was going to shift that line of rotation. This is your axis of rotation, about the line. I don't really like to make it solid. I like to make it dashed. So notice, step 1, I drew. Step 2, my axis of rotation. Step 3, my strip. But my strip doesn't go down. I know I'm still slicing perpendicular to the x-axis, but here is my slice. Here's the top. Here is the bottom. Next, draw your reflection. So again, I know this is a pretty little version, but this is me drawing the reflection. Oh, it's so bad. And then I'm going to spin. Go from the top, spin. Don't forget, I asked myself a question. This is not really an important question today because the answer is always going to be no, but next video, the answer might be yes. Between my function and the axis of rotation, is there any space? Even though I shifted the axis of rotation, there's still no space between my shape and my axis of rotation. Therefore, this is a potato chip or a disc problem. And when I do a disc problem, I need to still, I've sliced down this way. I still have the area of a circle. Pi r squared, it's the same function. Oh, it's the same function, but look at my radius. What the heck? What the heck? Remember, I need to write an area function in terms of x. That is pi times my radius squared. This is why you want to draw your strip. Your strip is your radius. What's the length of the radius? Right? And if it's hard for you to picture, just plug in a number. You know this is where y is always equal to 1. So y is equal to 1 here. What is it here? What is y equal to? How do you figure it out? You plug, right? You plug in your x here and you get your y. So that's why my radius now, oh, shift, right? The axis of rotation was shifted off the x-axis. I had to shift my radius then too. O shift. So square root of x, because remember, a function, if function is always defined, the height of a function always comes from the x-axis all the way up. Is that too big or too small for my radius? It's too big. How much do you have to take off? 1. Square root of x minus 1. It's another way to think of it. Notice my limits of integration weren't from 0 to 4 anymore, were they? This is the point of intersection. And they wanted me to stop at x equals 4, so that's right here. So start your slices at x equals 1. Stop your slices at x equals 4. Your area formula is pi r squared. Area times width gets you volume. My radius this time was the square root of x minus 1 squared. And I just did math 9 with this. I mean, I could have distributed and blah, 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 blah. But that's not x minus 1, right? You wouldn't just distribute the square. Notice I wrote 3 places past the decimal. And AP allows you to write equals there when you're using math 9. All right, so I did an example of using the same function, and the only thing that was different with example 2 was that I shifted the axis of rotation off of the horizontal x-axis. Now the next example, I'm going to make the axis of rotation the y-axis. So think about that. Find the region between the curve x equals and the y-axis. So here, what am I highlighting? Starting and stopping on the y-axis. The region is between this curve and the y-axis, and it is revolved. What is it revolved around? The y-axis. Find the volume. So this time, instead of my apple slice looking like this, it's going to look like this. Because this time, you're slicing across to the y-axis. So here is the shape. X is equal to 1 over the square root of y. This is the shape here. They told me to start low at 1 and stop at high at 4. And they told me the region between this curve and the y-axis. Question: is there any space between your shape and your axis of revolution? There's my axis of revolution. X equals 0. So I drew the reflection across my axis of rotation. And then I drew my strip from my function to the axis of rotation. This time I don't have top and bottom. I have right and left, but I still spin. There is my apple slice. Poorly drawn, but it is my apple slice. And then I'm going to click and drag, right? And I'm going to sum all of those apple slices up by figuring out the area of one. The thickness is dx. No, it's not. It's dy, right? Because every slice, right? Slice here, that's a change in y, right? So this time I need an area expression in terms of y. So that's pi, still r squared. Here is my radius. How, not tall is it, how long is it? I want to know when I plug in this y value of 3, what is the x value? So isn't it true that your radius is just the function? There was no shift off of the vertical axis, right? X is equal to 0. No shift, which means I don't have to shift the radius. The radius is just measured from the y-axis out to the function. That is the length of my radius. So start lowest y value, stop at the highest y value, 1 and 4, area, but because you're slicing onto the y-axis, these have to be y numbers, and your function needs to be in terms of y, which it is. That's a very nice, simplifies to 1 over y. Osmosis the pi out front. Remember, ln1 is just 0. So if I pi ln4, this answer is perfectly fine, but in multiple choice, they might write it like this using the law, right? Properties of logs. Sweet. Now, can you think to yourself, what would you do if I did a shift? What would you do if I gave you this same function here, but I said your axis of rotation was x equals -1, or your axis of rotation was x equals 3? No, I would not put an axis of rotation right through it. You still have the same, right, shape that is bounded by the function for y equals 4, y equals 1, and the y-axis. So you still have the same shape. But when you reflect, remember, you have to reflect across the axis of rotation. So I would have to draw this. Oh, it's terrible. There's my reflection across, right? Oh, shift. What's your radius? Remember, your radius isn't, right? The strip that you draw is from the function, the real function, not the image, to the axis of rotation. How far is that? Is it bigger or smaller than just this radius? Right? 1 over square root of y is right here. I need more. How much more do I need? +1. So O shift, a +1 would go in there. Right? I'll leave it to you to figure out if I had to go across here, what would I do? Right? But it's just a matter of picturing it. My drawings are terrible. I'm not a good drawer. This is beautiful, these little images. Some of you draw and just embarrass me when I go around, when if we're in person and I was looking at homework, or now when I'm going to download and look at your homework, I'll be embarrassed and I'll be like, oh, gee, those look so nice and mine look so terrible. It doesn't matter though, right? In reality, it doesn't matter how good my drawing is for this purpose. I just need to visualize what's going on. And what do I need to write? I am just writing an area function. And my cross section is just a circle. No big deal. All right, so that was 1 through 3. If you turn it over, I want to do one last example with you. Right? I have relatives who live in the Ohio Valley, right? And when I would go and visit my grandmother, I would always drive by these kinds of see these kind of plants, right? Power plants or whatever they are. But I want you to look at its shape, right? If I superimpose an axis on there, right? This is a draft cooling tower. It's about 500 feet high, so that's where I put the top. Its shape is approximately this graph right here. This blue graph is approximately the shape of 1/2. Notice it's an x equals equation in terms of y. Then I took this shape and revolved it around which axis? Is there a space between your axis of revolution and the function? No. No shift. They want me to find the volume by revolution, and I'm revolving around the y-axis. So I need to write a function where I need to write an integral where I am slicing at the y-axis, boom, boom, dy, boom, change y, boom, making another slice. How fortunate, since the function that describes this shape is in terms of y. So I said add up from y, the bottom, the ground, to 0. It is 500 feet tall, of the area pi r, oops, I forgot my squared, pi r squared dy. You can put this into y1. And then, yes, you're going to have to type x's, right? So just lie to your calculator. And do math 9 on this. Don't forget to multiply by pi, your answer, or leave pi in, right? Do pi times y1 if you want. Since they did give me units, I gave them units back, volume cubed. Okay? Not too bad. I'll see you in our next live session.